Yeah. I don't have any with me. Anybody have the problems? A printout. All right. So 2D kinematics number 6. So this is the one where an object is dropped from the window of a car. Um, and the height of the window is 1 meter, 0.8 meters, sorry. And the car is moving 15 meters per second. And so the object's held out the window, let go, and we want to know how far the object, so the object starts here, and we want to know horizontally how far it travels before it hits the ground. So we want to know what this distance is. This is another one where I think a lot of people's intuition would say that if no matter what you're doing, when you drop the thing, if you just hold something out and let go of it, it's just going to fall straight down. But that's not what happens. If you are moving 15 meters per second when you let go of something, then at that instant, when you release it, it's also going 15 meters per second horizontally. For the coordinate system, let's put it on the ground beneath where the object is when it's released. And the y-axis up. We have to choose the time equals 0 and the time final. These two are shown in the picture. Time equals 0 is going to be when the object's released. And time final is going to be just before it hits the ground. And so now we have to figure out what we know and what we want. Do we know the amount of time it takes to hit the ground, time final? No. Do we know the acceleration? Yes, it's in free fall. So AX is 0. AY is negative 9.81. Do we know the initial position? Yep. So PIX, what's the X component? 0, yep. And what's the Y component? Yep, 0.8, and that's positive. Do we know anything about the final position? Correct. What? Yep, exactly. So PFY is 0. PFX is what we're trying to find, so that goes over here. Do we know anything about the initial velocity? So VIX, VIY, we know both of these because we know that at the instant the object's dropped, it's moving horizontally with a speed of 15 meters per second. And so if you put the tail of that vector at the origin, you're just trying to come up with the coordinates of this point. So that's just going to be in the positive x direction, 15, and then 0 for y. So VIX is positive 15, VIY is 0. And we're going to treat it like we don't know anything about the final velocity. Is there an equation that works with this? No. So first we want to, so no equation works. So let's try to find TF and see if that helps us. Okay, so is there an equation that has TF in it and everything else in it is known? The one that works is PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. So 0 is equal to 0.8 plus VIY is 0, so this second term goes away, minus 4.905 TF squared. And so TF squared is equal to 0.8 divided by 4.905. And then you can take the square root of both sides. TF is equal to plus or minus. Can someone tell me what the square root of 0.8 over 4.905 is? You could, yeah. Usually, I mean, you never have to do the quadratic unless you have and a linear term and a square term. There's always a a way around it if you don't have all three of those. And you don't need to use the quadratic, it's usually easier. I mean, if you have it programmed into your calculator, it's no harder. So, anybody have that answer? What is it? 0.195 seconds, and we don't want negative time, so we want the positive. What? Yes. Oh, that's TF squared. Yeah. Can you take the square root of that? So 0.441, and we want the positive one. Okay, so now we know TF, so that goes into the column of things that we know, and we can use that to find PFX. So PFX is equal to PIX plus VIX TF plus 1/2 AX TF squared. So PFX is equal to 0 plus 15 times positive 0.441 plus AX is 0, so this whole term goes to 0. And so what do you get for 15 times 0.441? 6.615 meters. Any questions about that? It usually is the case, I don't know if you've noticed this, but it's usually the case that if you end up using the PFY equation to solve for TF as an intermediate variable, it's usually going to be the PFX equation that gives you the answer. That's just the way it usually comes out because of the way the given values usually come together. It doesn't have to be the case, but it's a pattern that you see if you do these over and over again. Any other homework questions? All right, so last time we started the new topic. So we started two-dimensional kinematics. This is of a particle. So we're still not dealing with rotations or objects with length dimensions. And we defined mass, and I said that we're going to think of mass as just a resistance to accelerations. And then I gave the most important equation for this whole class, Newton's second law. I'm going to always abbreviate that N2L, Newton's second law. And Newton's second law says if you add up all the force vectors acting on an object, so we're going to call that F net, that's equal to the mass of the object times the acceleration of the object. So this F net is the sum of all forces acting on the chosen object. And m is the mass of the chosen object. And a is the acceleration of the chosen object's center of mass. And we started to define forces. We started to talk about forces. I did say that forces in this class are going to be broken up. Well, I think maybe you could say just generally. It doesn't have to do with this class or other classes. Forces can be broken up into two categories. The first one is the weight force, the force applied by gravity. Really, that's the weight force is a subset of force fields. And so gravitational force is a force field. There are some other types of force fields like electric fields, magnetic fields. We're not going to talk about any other ones except gravity. But if you think of those as one category, then that's the first type of force we'll deal with. And the second one, and these two categories account for every force that we're going to deal with, are contact forces with other objects. From touching objects. And I think this is a really useful way to think about it because we're going to get into complicated problems where it can often get a little, like you first glance at the problem and you're asked for like what kind of force is being applied to the thing by this. And there's a lot of things going on and it can be sort of complicated to intuitively you look at it and you're like, how am I going to know when I've accounted for all the forces? Well, if you think of it this way, it's easy to know when you're done accounting for the forces. You're going to account for the weight force that gravity applies to things, and then you're going to go around the boundary of your chosen object. Like say your chosen object is the wheel of a car. you're just going to go around the boundary and look at any place that outside objects are touching the boundary. And you know at each one of those contact places, there's a force. And once you've accounted for all those contact forces, you're done. Okay, so it's a nice sort of centering technique, you know, like it's a nice way to break the problem down into just a sort of a systematic approach to getting through all the going through all the forces. Okay, so let's start talking about the different kinds of forces, how you know what kind of force vectors are applied. So first, let's deal with the weight force. And weight is the force applied by gravity. And we're going to be able to figure out what the weight force is applied to an object by analyzing an object that's in free fall. So to figure out the weight force on an object, let's consider an object with a mass of m, lowercase m, in free fall. Okay, so here's our object with a mass of m. And what do we know about something that's in free fall? Yeah, so if it's in free fall, we know that the acceleration vector is 0 for x, negative 9.81 meters per second squared for y. That's if we have our y-axis pointing up. And so think about the definition of free fall. What forces are acting on an object that's in free fall? Gravity, and that's it. That's the definition of free fall. And we also know that the only force acting is the weight. Okay, so based on that, let's fill in Newton's second law. So Newton's second law says add up all the force vectors acting on the object, and that's just a force vector of, well, so I'm going to write that as the force of the weight. I'm going to break it up into x and y components. That's what we're going to calculate. And that's equal to the mass of the object. We said we're dealing with a mass m, so mass times the acceleration of 0, negative 9.81. And now we can break this up into two separate equations. The x and y equations, what's happening in the x component doesn't have any effect on what happens in the y component and vice versa. So I'll break this up into an x component equation that says F sub W x component is equal to 0 times m. So that's 0. And the y equation says F sub W y component is equal to negative 9.81 m. And a lot of times you'll see that written as negative mg, where that g is 9.81 meters per second squared. Okay, so what this tells us is gravity applies a force magnitude of mg down to an object with mass m. And we use free fall conditions to calculate this. But this is true whether the thing's in free fall or not. So this is a force applied to an object no matter what else is happening to the object. Okay, so I want to take a minute to talk about this in relation to the common misconception number 1 that I talked about. So how does this relate to common misconception number 1? Okay, so what is common misconception number 1? That's right. So I think the wording I used was something like gravity makes a larger mass accelerate faster. And it turned out that no, gravity doesn't do that. When that does happen, it's just because air resistance slows down the less massive thing more than the more massive thing. So if there's no air resistance, objects accelerate down at an acceleration of g, 9.81 meters per second squared, regardless of the mass. But look at what this result just said. We just calculated the force that gravity applies to things. So now we see that the force gravity applies to objects is proportional to the mass. Okay, so the question is, how can both of those two things be true? This is a super confusing thing. So if you go into that vacuum chamber and drop a bowling ball and a feather, and they both accelerate down at 9.81 meters per second squared. Now we calculate the force that's applied to those, and the bowling ball has a much bigger force applied to it than gravity does. So how can these two things both be happening? Yep, that's exactly right. Yep. So like the way this works is, since mass is resistance to acceleration, okay, if you had a bowling ball and a feather and you wanted them both to accelerate 9.81 meters per second squared, you'd have to apply a bigger force to the bowling ball. It has more resistance to acceleration. Okay, you need to apply a bigger force to overcome that. And so that's the relationship between these things. Gravity, so it seems like sort of a paradox or something at first when you, if you're, before you've thought about it this way. But both of these two things are true. Gravity does apply a bigger force to things with more mass, but gravity doesn't make things with bigger mass accelerate more. So let's see. How can that be? And the answer is mass is resistance to acceleration. So to make two objects accelerate down at 9.81 meters per second squared, gravity has to apply a bigger force to a more massive object. Any questions about that? Yep. Acceleration. Yes, that's right. So think about uh, think about a skateboard and a car in neutral sitting in the parking lot, um, and say that you're going to push on both of them and make them accelerate at a, they're each going to have the same acceleration. Okay, so imagine the car, you have to push pretty hard to get it moving. The skateboard's really easy. Well, you're going to have to apply a much bigger force to the car to make it accelerate at 1 meter per second squared than you are on the skateboard. And it works the same with gravity. Yes. Yes. So the misconception is that people often have the idea that objects with more mass are accelerated more by gravity than objects with less mass. The truth is that if you get air resistance out of the picture, like in a vacuum chamber or whatever, or you just deal with things that aren't affected very much by air resistance, no matter what the mass is, two objects in free fall accelerate down the same at 9.81 meters per second squared. So the differences that you're used to, like you're used to seeing a bowling ball and a feather fall at very different accelerations. The bowling ball falls and the feather floats down. But that's only because of air resistance. But now we find out that gravity applies different forces to both of them to make that happen. All right, so now we already have one thing we figured out. That's great. Now let's figure out here's an example problem. Let's say that there's a scale sitting on the floor and a man standing on the scale. And let's say the man has a mass of 100 kilograms. And we want to know what's the force vector applied to the man by the scale. Okay, well, Newton's second law says that we're going to add up all the forces acting on the man. So that's what we're calling the net force. And that's going to be equal to the mass of the man times the acceleration vector of the man. So this is the sum of all the force vectors. On the man. So the man is going to be our chosen object. The mass of the man is the mass of the chosen object. And this acceleration vector is the acceleration vector of the man, the chosen object. And let's use a coordinate system like this. Okay, so what forces are acting on the man? Well, gravity is always acting on anything. And now we know that the force of gravity, so let's break it up. The force applied by gravity, the weight, is equal to 0 in the x direction. It's always a downward force, so then negative 9.81 times 100, so 981. And the units are newtons. We're doing everything in SI units. So this negative 981 comes from negative 9.81 times 100. And to figure out any other forces acting on the man, we have to think about like the man's boundary. Just imagine going all the way around the boundary looking for contact with things that are not part of the chosen object. So you go around, nothing, 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 and then you get to the scale. The only contact is between his feet and the scale. So the only contact force is the force applied to the man by the scale. Any questions about that? And then do we know anything about the acceleration? Well, we're imagining that he's just standing there, so he's not moving at all. then there's no velocity, and if the velocity never changes, there's no acceleration. So the acceleration vector is 0x, 0y. And now we can put this all into Newton's second law. So the sum of the force vectors is 0, negative 981. The force vector applied by the scale, we don't know what that is, so I'm just going to call that F scale, break it up into an X component and a Y component. We have to calculate both of those. By the way, just notation-wise, when a variable is a vector, put the vector symbol over it. But when you're talking about the individual components, you don't, because, like, for example, F scale X is just a number. Okay, so that's just a single variable. Same with this. Okay. And those are equal to the mass of the man, 100 kilograms. So on the right side is the mass times the acceleration, and then the acceleration vector of 0, 0. And now we can break this equation up into an X component and a Y component. The X equation says 0 plus F scale X is equal to 100 times 0, so 0. And this, this is an ugly name for a variable, but I just gave it this long name so you can keep track of what it represents. But I mean, that could just as well be X or whatever. We're just going to solve for that. And so F scale X is equal to 0. And then the Y component equation says negative 981 plus F scale Y is equal to 100 times 0. And so F scale Y component is positive 981 newtons. So to put this all together into a force vector, the force F scale vector has a 0x component and a y component of positive 981 newtons. And then, in other words, if this is the coordinate system, plot that point. So go 0x, positive 981y. You get a vector that looks like this, magnitude of 981. So another way to say this is a magnitude of 981 newtons. Okay. So the force is applying, scale is applying a force of 981 newtons up on the man's foot. Feet. Yes. Here on when I first wrote Newton's second law, the force of gravity is down, and the magnitude is the mass of the chosen object times 9.8. His mass was 100 kilograms, so 100 times 9.81 is 981. Okay, so that's how a bathroom scale works, So you're not really trying to, like, you don't really care how much force the bathroom scale is applying to your foot. You really want to know is how much force gravity is applying to you, because that's proportional to your mass. And the way you use a bathroom scale to calculate, you have this thing that measures the amount of force it applies to your feet. And you get on it where the only two forces acting on you are the scale and gravity, and then they have to be equal and opposite. They have to be the same magnitude in opposite directions. Okay, so say you want to lose weight. So what can you do to lose weight without diet or exercise, or without waiting a whole bunch of weeks and stuff like that? That's a pain. There's no C in exercise, I don't think. Exercise. Okay. So we're going to do the same thing again. So same question, but this time the scale and the man are on an elevator that's accelerating down at, let's say, 2 meters per second squared. Accelerating down at 2 meters per second squared. Okay, so here's the elevator. It's accelerating down at 2 meters per second squared. And on the elevator is a scale. And here's the man. You probably shouldn't ride an elevator in your underwear like this, but. Okay, so what's the force applied to the man by the scale? All right, well, we're going to use Newton's second law. So F net vector is equal to the mass of the man times the acceleration of the man. F net is the sum of all the force vectors on the man. M is the mass of the man. A is the acceleration of the man. Okay, so let's figure out what we know about this stuff. For the sum of the forces, first there's the force applied by gravity, the weight force. And do we know what that is? Yep. So the fact that he's on an elevator doesn't have any effect on that. Gravity just always does the same thing. So that's going to be equal to 0, negative 981. And the units for force are newtons. The mass is 100 kilograms. And what do we know about the acceleration of the man? That's right. So he's just riding the elevator. So whatever the acceleration is of the elevator, that's the acceleration of the man. So this is equal to 0, negative 2 meters per second squared. So Newton's second law says, well, what forces are acting? The gravitational force is acting, 0, negative 981. And now we have to think about all the contact forces. Where is the outside world in contact with the chosen object? Just the scale. Nothing's changed about that. So we still just have F scale X and F scale Y. And that's equal to 100 times the acceleration, 0, negative 2. So the X equation says F scale X is equal to 0. I guess to expand on this, the X equation says 0 plus F scale X is equal to 0. So F scale X is equal to 0. And the Y equation says negative 981 plus F scale Y is equal to negative 200. And solve for F scale Y, and you get positive 781 newtons. So if you write this as a force vector, the force applied to the man by the scale is 0, 781 in newtons. Or another way to think of that is 781 newtons up. Okay, so I want to lose 200 newtons of weight according to the scale, get on an elevator accelerating down at 2 meters per second squared, and the scale will read this lower value. That's the same thing, like you kind of know that this effect happens because you can kind of feel it in your stomach when the elevator starts to accelerate down. Then when it gets up to a constant speed for the rest of the trip down, you don't feel anything. At that point, the acceleration's 0. So this would only happen right at the start of that motion. Yep. Mm-hmm. Uh, the effect of altitude is pretty small on gravity. The acceleration of gravity just based on altitude alone at the top of Mount Everest. Well, so at sea level, it's 9.80655. At the top of Mount Everest, it's something like 9.804 or something. It's really close to the same thing, even though that's a difference of 9,000 meters or something. So it shouldn't. I wonder if that's some kind of like magnetic effect that you're noticing based on electrical currents going through the wall or whatever. I don't know, but yeah, the altitude changes inside a house are tiny. You wouldn't notice anything. Yep. Hmm. Right. Um, no, that means that if you isolate the man, um, all of the forces add up to zero for the acceleration to be zero. And actually, what you're talking about is kind of a we'll talk about that that way of thinking about it. It's a if you think about it that way, which is sort of a natural thing to do, it can lead you to a lot of wrong answers. So what you want to think is like you choose one single thing to isolate, and then you apply Newton's second law on that one single thing, and that's all. Um, and then you could isolate the scale too, and the scale would have its own weight. You know, say it weighs 1 kilogram or has a mass of 1 kilogram acting down, and then there'd be a force that your feet are applying to the scale, and then there'd be a force up that the ground is applying to the scale. And when you added up all three of those forces, those would have to add up to zero for the scale to be at rest. If those didn't add up to zero, it would mean that the force pushing up from the floor wasn't enough to counteract those two weights, and that means the floor breaks and you go down. So hopefully that doesn't happen very often. And what do you think happens if you're on the scale and it's accelerating up at 2 meters per second squared? Yeah, the scale would read a heavier, it would read 981, right, plus 200. So, yeah, if you're ever, you know, you're like trying to fit into your dress for the prom or whatever, propose that they do, if they did the whole prom accelerating down at 2 meters per second squared, well, your dress still wouldn't fit. That's true. um, yes. For F net, that's right. Yep, that's right. The weight is still the same. The weight is the force that gravity applies, and that never changes. What changes is just what the scale reads. Um, okay, and the next thing we're going to talk about, let's not start this today. Um, it's free body diagrams. I'm going to abbreviate that FBDs. And drawing FBDs, we'll draw one of these every time we use Newton's second law. And what it is just a way to make sure that you're taking into account all the objects acting, all of the forces acting on an object, and to make sure that you're being consistent about what you're calling your chosen object. So the first thing it's going to do is make you be consistent about what is your chosen object. And the second thing it's going to make it easier to do is bookkeeping with your forces. with the forces applied to the chosen object. So for example, if you want to figure out something about the forces that are happening when a baseball bat hits a baseball, and you just sort of do it loosely in your head, it can be pretty easy to jump from thinking about one thing to the other thing. Maybe you think of the mass of the bat and the forces acting on the bat, but then you think of the acceleration of the ball. And if you do that, everything goes haywire. You need to be consistent about what's your chosen object through the whole thing. So that's sort of the goal of this. Anybody have any questions, more questions about any of this? Okay, we'll do that Wednesday.